All right, so now we're getting into 7.2, and this is where we're going to start learning about a few new formulas that you're going to need to memorize, or have a sheet and know how to write them down, or at least recognize them when we're working with equations. So what this one's on is compound angle formulas. Compound means when we add or subtract two angles together. So compound angles by adding or subtracting. So there's 6 special angle formulas that we're going to need to know called compound angle formulas to help us determine the exact values of the sums or differences of angles. So if you look at the way that the formulas are written, all the sums are on the left side and all the differences are on the right side. Now the same ratios appear in the same spots. It's just the signs that change between additions and subtractions. So for sine, if we're adding two angles together, that's equivalent to sine of the first angle, cos of the first angle. Now that's a multiplication between those two because we're not, there's no sign in between them. And we add sine B cos A, or beta and alpha. So notice the formula of how they show up. The subtraction is the exact same. The only difference is there's a subtraction between. So the sign stays the same between them. So we have sine cos minus sine cos, but the angles switch. Cosine is similar. The difference is we have cos alpha, cos beta, minus sine alpha, sine beta, or AB. Doesn't matter what we refer to it as. X, Y, doesn't matter. One thing about cos is that the sign is different in between. If we're adding two angles together, the formula has a subtraction. And if we're subtracting, the formula has an addition in it. And finally, tan down at the bottom. If we're adding two angles together, we have on top tan A plus tan B. So the sign stays the same on the top, but is different on the bottom. Same goes for the one over here on the right. The sign is the same on the top, right? It was negative, so we're subtracting, so still subtracting on top. But the difference is we're adding on the bottom. It's the opposite. So it's a matter of just memorizing these ones or working with them enough that you start recognizing to see where they show up. So the idea is, why do we have these compound angles? What's the point? Well, right now we know how to find exact values for pi over 6, pi over 4, and pi over 3. So what angles are those? Well, pi over 6, we know how to find exact values of 30 degrees, 45 degrees, and 60 degrees. We also know how to find out exact values for these when they appear in other quadrants. Like, for example, if we have a related acute angle of pi over 6 here, right, 30 degrees down in that corner, I know how to find out the exact value for 150. Or if it's 45 in the second quadrant, I know how to find out the exact value of 135. And finally 60, I know how to find the exact value of 120. And we can continue that along the third quadrant as well. If I find out the exact value of 210 degrees, or if I find out third quadrant of 225, or third quadrant of 60, which is 240. And we continue that at the fourth quadrant if we want, but the idea is these are the exact values that we know how to find right now. What we do when we come up with compound angles is to find out the exact values of combinations of these. So for example, I could find out the exact value of 135 minus 30. So I can find out the exact value of 105. Right, that would be subtracting. I can find out the exact value if I added them. 165 degrees. I can do that. And that can be done with any of these angles that we have, right? If I want to find out the exact value of adding, let's say these two together, 270 degrees, for example, I could find out the exact value of some of those using the formulas that we have up top. where A would be one angle and B would the other. So what we're going to do is we're going to end up getting some angles. I might say, I want to know what's the exact value of sine 195. And you're going to have to think, which angles could I add together which would give me 195? You might say, well, I see this one here and I see this one here. They add together for 195. So I'm going to change this into sine 135 plus 60 degrees. And that would be considered alpha beta. I'd be using the sine addition formula. And I would break that down into sine alpha, which is 135, times cos 60, plus sine B, which is sine 60, and cos 135. Where each of these are exact values that we know how to solve. We didn't know how to solve for sine 195, but I can find each of these. I can get the value here, multiply it by the value here, and then add that result to the multiplication of those two values on the end. And we're going to go through some examples like that. But that's the idea behind these exact values and why we end up working with them. So it's kind of an important skill for us, and you'll see when we look at some examples down below. So write the following as a single trig ratio. So I have sine cos, cosine. I know that that's a sine. When it was cos, cosine, sine, that was a cos, compound angle. This is a sine, compound angle. And because it's adding, I know that sine is going to remain the same. We're going to still be adding two angles together. Here's my alpha, beta, beta, alpha. So I need to add those ones together. I'd be adding 3a plus a. So if I'm writing that expression at the top as a single expression, it'd be sine 4a. All right, let's continue with the one for tan over here on the right. So tans are easy to identify because they're the ones that have tan in it. So this is a tan formula. And I know that a compound tan formula has the same sign as what's on top. So I know it's going to be tan adding some values. We have alpha, beta here, alpha, beta. So we're adding together 3 plus 5, which is tan 8. So I can simplify that to just tan 8 radians. So if we can identify those, we can solve for some unknowns. So these ones have us, for question 2, write the following as a single trig ratio and then evaluate. So first, when I'm going to look at this, I see sine cos, cosine. That's an identification that we're dealing with sine. I see that we have a subtraction, so I know I'm subtracting the two angles together for sine. And the two angles we have are pi over 2 and pi over 3. So if I want to simplify this, maybe I get common denominators here. So maybe I change this into sine. Common denominator would be 6 for both of them. First one would become 3 pi over 6, that's half. Second would become 2 pi over 6. And we subtract them together. I get sine pi over 6. I can find an exact value for those. If you're not sure, you can use your special triangles. Right, we have pi over 3, pi over 6, root 3, 1, and 2. And sine of pi over 6 is opposite over hypotenuse, 1 over 2. So we get half. I could have used that special triangle that I had mentioned to you before as well. If you want to draw out that first quadrant I had mentioned to you before, where you could say, well, this is pi over 6, this is pi over 4, this is pi over 3. And if I want my xy coordinates, when we go from the top, 1, 2, 3, all of those over 2, and we square root the tops. Square root of 1 is 1, so it stays the same. And then I go in opposite direction for the y values. Square root the tops, keeping in mind that sine were the y values and cos were the x values. So in this case, I was looking for sine, which is the y value, of pi over 6. So pi over 6 is right here. The sine of the y of that is 1 over 2. So that's another way that we could get it using, that's just from the unit circle. I'd mentioned you can use that You just have to keep in mind the cast rule of where things are positive and things are negative. But that's one method. So let's keep going. So whether you draw the special triangle or use that unit circle, both are fine. Next one, I see tan. So I know we're dealing with the tan ratio. I see that it's an addition happening. So I know it's some angle adding together. Our two angles are pi over 2 and pi over 6. So I have to get common denominators here as well in order to add these. So I would get 3 pi over 6 plus pi over 6, which when I add them together, I'm going to get 2 pi over 3, right? Or 4 pi over 6, which can be reduced to that. Next, I want to find out what is my exact value for tan 2 pi over 3. Well, that's in the second quadrant, so I know it's going to be negative. And if we're not sure, you can use your table and say, well, I know it's going to be over here with a related acute angle of pi over 3. You can use the exact value, whichever method you're happy with, but essentially it's going to be opposite over adjacent for pi over 3. So our values are going to be root 3 over adjacent, which will be 1. So negative root 3. I could go through and solve each one of these ones and solve it through, and I'm going to get negative root 3 in this case as well. So it doesn't matter which method we use to get there. All right, keep rolling along here. Determine the exact value of 5 pi over 12. A few different ways you can go about this. You could think about 5 pi over 12 and try to think about it in degrees, right? So convert that to degrees. If I was to do that, you would get 75 degrees. So that's not a normal angle that we're used to. So if I go back up to our chart and I say, well, how can I get 75 from what we've got here? Well, there's a few different ways you can do that. One of the ones you're probably going to look at is I can add together pi over 6 and pi over 4, or 30 degrees and 45 degrees, right? The sum of those would be 75. So I'm going to add 30 and 45. So I'm going to do it both in sine and in radians. You would choose sine 30 plus 45. Or if I'm doing it in radians, 30 degrees in radians is pi over 6 plus pi over 4. So if I'm solving this one through, you're going to use the sine addition formula. Now, if you remember the sine addition formula, I'll write it out. You don't have to do it every single time, but sine alpha plus beta is equal to, remember, sine has opposite ratios. Keep the same sign. Sine beta cos alpha. So whether I'm using radians or degrees doesn't matter. In this case, maybe I'll use radians. I know that we're going to be, so sine pi over 6 plus pi over 4 is equal to sine pi over 6 cos pi over 4 plus sine pi over 4 cos pi over 6. And it's just a matter of finding our exact values for these. So whether I use my special triangles, right, or pi over 6, we're going to have 1, root 3, and 2. So sine of pi over 6 is 1 over 2. That's being multiplied by cos pi over 4. You can use a special triangle for pi over 4. It works out to be root 2 over 2. We're going to add that together with sine pi over 4. That's also root 2 over 2. And cos pi over 6. That's root 3 over 2. And just use the matter of using algebra. Multiply my numerators, root 2 over 4, plus multiply my numerators, root 6. Remember, when you multiply roots, you can multiply the numbers underneath the roots. They're both square roots, so 2 times 3 I can get root 6 all over 4. and I can add across the top. We can't add roots. They're like treated like unlike terms. So that's as far as we can break this one down to. Root 2 plus root 6 all over root 4. That's the exact value of sine 5 pi over 12. So let's keep going along here. Tan pi over 12. How do we get that? Well, maybe we think of this in terms of degrees as well, if that's what you're most familiar with. In order to get degrees, I'm going to have to put 180 divided by 12 because the pi's will cancel out. I'm looking for tan 15 degrees essentially. So let's think about our exact values that we know. I want 15 degrees, so it does not matter how I get there. I can take 60 minus 45. Subtract those. Or I can take 45 minus 30. Subtract those. Does not matter. So choose one or the other. Maybe I'll choose 45 minus 30 for that. So let's go back down to the question. I'm going to rewrite this as tan 45 degrees minus 30 degrees. I want the exact value of tan 15, but I'm going to break it down to exact values that I know. I know 45 and I know 30. I could write it as radians. Tan 45 degrees is pi over 4 minus 30, which is pi over 6. So let's go through this. We're using a tan compound formula, the subtraction of tan. So what does that equal to? Well, the formula, if you forgot, tan alpha minus beta, you don't have to write this every time, you can see it above, is tan alpha minus tan beta all over 1 plus tan alpha tan beta. And on the bottom, they're multiplying. On the top, they're subtracting. So let's fill in the values that we know. I know tan pi over 4 minus pi over 6 is equal to, on top, tan pi over 4 minus tan pi over 6 all over 1 plus tan pi over 4. So in this case, I'm only needing to find two ratios. I'm needing to find tan pi over 4. I'm needing to find tan pi over 6. That's all we've got. So I did not know what 15 degrees was, but I have a formula using exact values that I know. So on top, I need to find out what tan pi over 4 is. So if you're not sure, you can go back to your special triangles. Pi over 4 was 1, 1 root 2. So tan pi over 4 is opposite over adjacent, which is 1 over 1. So I'm going to have 1 minus something. On the bottom, I'm going to have 1 plus 1 times something. So the next one I need is tan pi over 6. So if we're not sure, once again, you can use your unit circle, your special triangles. Doesn't matter how you get there. But if we have pi over 6 and pi over 3, we're going to have tan pi over 3 is root 3, 1, and 2. Tan pi over 6 is opposite over adjacent, so 1 over root 3. So I need to simplify what we've got here. We have a numerator of 1 minus root 3 over 1 over root 3, or 1 minus root 3 over 3. I have a denominator of 1 plus root 3 over 3. I want to simplify what we've got here. So I can do a little bit of algebra, get common denominators. So like for my numerator, if I got this to be 3 over 3 instead, and for here to be 3 over 3 instead, we would end up with something that looks like this. I would have 3 minus root 3 over 3. That's the numerator. And it's being divided by 3 plus root 3 over 3. And if you remember, when you divide, it's like multiplying by a reciprocal. Essentially what's going to happen when I divide those, or multiply by the reciprocal, right? I can flip this. 3 will be on top, 3 plus root 3 on the bottom, and multiply. The 3's will end up 3 minus root 3 over 3 plus root 3. Now that's the answer, but do we always work with that? There's always a better way to display a fraction that does not have a radical on the bottom, that root 3. We don't want that root 3 on the bottom. So one thing that you learned last year in order to get rid of it was to what we called rationalize the denominator, and we can do that by multiplying by its conjugate. A conjugate means keep the numbers the same, but change the sign that's in between. I can do that to the top and bottom, no problem. It's like multiplying by 1. Multiplying top and bottom by the same thing. So if we do that, that's like having 3 times 3, which is 9. 3 times negative root 3, which is negative 3 root 3. Negative root 3 times 3 is also negative 3 root 3. And then finally, negative root 3 times negative root 3 is positive 3. All of that over, do the same thing on the bottom. 3 times 3, 9. 3 times negative root 3, negative 3 root 3. Then positive 3 times, root 3 times 3 is plus 3 root 3. And then positive 3 root 3 times negative root 3 is negative 3. So on the bottom, what's going to happen? These numbers will end up canceling out because one's positive and negative, the exact same thing. My denominator will be 6. On top, I can add the 9 and the 3 together to get 12. I can subtract these to get negative 6 root 3. And then I can take out a factor of 6 from each of them. Right, 12 divided by 6 is 2. Negative 6 divided by 6 is negative 1 root 3, or just root 3. And that's how we can simplify our answer. Right, that's just multiplying by the conjugate. Now that was a lot of extra work down at the bottom there, but that's how we can find the exact value of tan 15, or tan pi over 12. Cos 13 pi over 12 is. Now, in terms of degrees, that's equal to cos 195, if that's what you use. I want to find out from the exact angles that I know, how can I make 195 degrees from it? So I'm going to go back up to our exact angles that we know. And there's a few different ways. I could add together 60 plus 135. That adds together for 195. I could subtract 225 and take 30 away from it. That would give me 195. So either of those ones are okay. What I'll do is I'll use the addition just because I saw that one first. And 60 degrees, I know in radians is pi over 3. 135 degrees in radians is 3 pi over 4. Maybe the second quadrant with a related acute angle of pi over 4. So I want to add those together, 3 pi over 4 and pi over 3. So let's go back down to our work. Because 13 pi over 12 is not an exact value that we know, I need to use my compound angles. 3 pi over 4 plus pi over 3. Keep in mind, it doesn't matter which order I put them because when I add these together, order doesn't matter when you're adding. If you're subtracting, definitely need to have the bigger angle first if that's the case. So, cosine. I know that its formula, well, even before we start the formula, I can always check to make sure I did this properly by adding together what we have to see if it adds together for 13 pi over 12. If I get common denominators here, I would get 9 pi plus 4 pi, which add together for 13 pi over 12. So I know I did that right. I know we can start. So let's go through. I'm working with the cosine compound angle, the addition compound angle for cosine. Now remember, cosine had the same ratios on both sides. Cos 3 pi over 4, cos pi over 3, minus, it had an opposite sign. And the signs were on this side. And sine pi over 3. So I'm going to have to get 4 different ratios here. And I'm going to subtract the ones that we're going to multiply these two together when we get them, and I'm going to subtract it from these two when we get them. So let's start with cos 3 pi over 4. I know that in this quadrant, 3 pi over 4 has a related acute angle of pi over 4. I know that cos 3 pi over 4 in this quadrant should be negative, because that's where sine's positive in the second quadrant. And cos is root 2 over 2. I guess it's negative cos pi over 4, which is negative root 2 over 2. We'll put that step in there. So that first ratio we have is negative root 2 over 2. That's going to be multiplied by cos pi over 3. If I use my special triangles, I know that's 1/2. Subtract that from sine 3 pi over 4. So I'm going to use this same picture that we have down at the bottom. Sine 3 pi over 4. Well, sine is positive in that quadrant of sine pi over 4. And using my special triangles, I know that sine pi over 4 is root 2 over 2. So we have root 2 over 2. I'm going to take this off at the bottom. We don't need this again. And then finally, sine pi over 3. Sine pi over 3 is root 3 over 2. Use our special triangles. Now it's just a matter of using our algebra to solve this. So across the top, I'm multiplying. Subtract root 6 over 4. And I cannot subtract root 2 and root 6. They don't have the same index number. They have the same root. It's 2 out front, right? It's a square root. But they do not have the same number underneath the root, the radicand. So I cannot work with them. So I just keep them as root 2 minus root 6 all over 4. And that's the exact value of cos 13 pi over 12. All right, let's keep going here. This one we want the exact value of this equation. So what we could do, we know what the exact value of each of these are. I can substitute them in if we want to. Now in this case, if I wanted to substitute in sine of pi over 2 is 1. Cos of pi over 3, I know that cos of pi over 3 is 1 over 2. That's going to be subtracted from cos pi over 2. Well, that's 0. And sine pi over 3. It's root 3 over 2. So if I was to solve this, it would just be left with half. Because 0 times root 3 over 2 is 0. So I can plug those ones in because these are values that I know. Remember how we found out that sine and cos pi over 2. You might say, well, how do you get that one so quickly? Well, pi over 2 is right along the y-axis. And the unit circle has a point of 0 and 1, where cos is the x values, sine is the y values. So sine of pi over 2 is 1. That's how I got that first number. Cos of pi over 2 is 0. That's how I got that second one. So I could use that. But just to show you that it's the same when I use my compound angles, you might look at this and say, well, this ratio is a sine subtraction ratio, or formula. We're subtracting pi over 2 and pi over 3. And if I simplify that, with common denominators, I would have 3 pi over 6 minus 2 pi over 6, which is sine pi over 6. Now, if I use my special triangles for sine pi over 6, I also find out that works out to be half as well. So sometimes I can just substitute right in if we want. It's a little bit faster if you don't know your special triangles to convert it into a single ratio, which is this, and find the answer. But sometimes we're going to get angles that are not nice ones that we're not used to working with, where I'm going to have to convert it. And there'll be another one like that as we continue. All right, last one that we're going to do. It's kind of a twist on what we've been working with. Next one, it says evaluate sine A, B. So it's an addition. So it's saying I know that sine A plus B is equal to sine A cos B plus sine B cos A. That's the formula. And then it says where A and B are both in the second quadrant. A and B are both in the second quadrant. So let's take angle A to start. That's our angle that we're working with. And it says for A, sine is 3 over 5. That means the opposite from A is 3. The hypotenuse is 5. I don't know this side, but I can get that using the Pythagorean theorem. 5 squared is equal to 3 squared plus, in this case we'll call the bottom x, because it's along the x-axis, squared. And when I solve it, I get 25 minus 9 is equal to x squared, which is 16 is equal to x squared. And I get x is equal to positive or negative 4. Now, because we're to the left here, I know that x is going to be negative 4. So I'm going to use a different color to show that we found that one, but it's to the left, negative 4. So why do we go through all that? Well, now that I have this picture here, I know that I can find out sine of A, 3 over 5. I can find out cos of A, negative 4 over 5. And I can find out tan of A, 3 over negative 4, opposite over adjacent. So I'm going to do the same thing with angle B. Maybe I'll do it below to save myself a little bit of room here. Whoops. Angle B is also in that quadrant. It says it's in quadrant 2. What do I know about angle B? Well, at the top it says sine is 5 over 13. So it means we have 5. It's the distance down. Hypotenuse is 13. And I can find out my x value here as well by using Pythagorean theorem, because I know 13 squared is equal to 5 squared plus, in this case, x squared again. We get 169 equal to 25 plus x squared. We get 144 is equal to x squared. And finally, x is equal to positive or negative 12. But now, since we're to the left, I know that we're talking about negative 12. Oops. We have negative 12. So that allows me to find sine, cos, and tan from that angle A. I know all three sides of that triangle of the terminal arm. So let's know what we know. So sine of A is the first value that we want. While I look at angle A, sine is 3 over 5. That was given to me. Didn't have to do any work for that. Cos of B is being multiplied by that. Well, that's have to look down this angle here. Cos is negative 12 over 13. Plus sine of B. So angle B, the one at the bottom, sine is 5 over 13. That one was given to me. And then cos of A. Angle A is at the top. Cos is negative 4 over 5. Right, it's important to make sure those are negative because it tells us that it's in the second quadrant. Right, the fact that it says it's in the second quadrant means that both coses will be negative. And when we keep in mind the x's, like we did, as being negative to the left, it'll take care of that for us. And then what I'm going to do is solve these ones through. When I multiply, I'm going to get negative 36 over 65 plus negative 20 over 65. And when I add them together, we get negative 56 over 65. That would be the exact value for that particular question. And there we go. So if there's any questions about these ones, there are some questions down at the bottom here for you to try. This takes practice in order to recognize the types of formulas that you'll see, but nothing that you can't handle with a little bit of practice.